Hello guys, I hope you're all doing great. In this video, I would like to talk about the last sense category of Aubrey de Grey's book in terms of defeating aging. This is actually pretty cool. I'll talk about mutations. Now, most of you guys know about mutations, right? And as well as epimutations. So mutations are simply changes to the DNA structure. And so then we have epimutations, which are just changes to the scaffold around the DNA. And so we know that if there's a mutation, it's going to cause changes in gene expression. It can either increase it or decrease it. It can either upregulate or downregulate gene expression, as well as it can affect the conditions at which its production, at which the activation of its production takes place, as well as it can affect the ensuing protein. So the protein that gets produced, right, its structure and function can also get impacted. And so the most noticeable example of mutations, you guys probably know, is cancer, right? And so in cancers, the cells accumulate a series of mutations which make them replicate indefinitely. And so that's a problem because that's actually something that could in fact kill us within a lifetime, right? And so that's what that's what he targets. That's what Aubrey de Grey is trying to target when he talks about mutations, specifically cancer, right? So like tumors and cancers, because what was actually shown is that there is not enough mutations to affect our health as we have good defenses. So every time, even if we have mutations, we have a very good repair system, the DNA repair, that's super effective. And so it's evolved to be super, super effective. And so essentially, what happens is most of our cell replications take place in our youth, in our early years. And it's really in these replications that mutations take place, right? Mutations occur when the cell replicates because its DNA duplicates. And that's where mutations take place. And because most of our cell divisions take place in our youth, and very, very few as we go older, our cells divide less and less, the risk of mutations occurring is less and less. So, and so therefore, mutations don't really affect us when we get older, except cancer, right? If a cell accumulates a series of mutations to the point where it goes crazy and divides and it grows into a giant tumor that can spread to the rest of the body, that is a problem. But other than really causing cancer per se, mutations are shown to be pretty harmless, especially since we have a very good DNA repair mechanism and because our cells don't divide as much as we get older. Hopefully this reasoning makes sense. But cancer is of course a problem because if a cell accumulates enough mutations to the point of to the point of dividing indefinitely, for example, if you get telomerase activation, we'll talk about that in just a moment, then that can cause a problem where because the cells divide so much, they can eventually undergo metastasis, right? And go to other parts of the body. Now, there's also types of mutations that are non-cancerous, senescence and cell loss. But we have already discussed how to deal with those in previous videos. And so senescent cells, for example, all we do is we have to destroy them, right? Using suicide genes. We talked about that in the previous video. And for cell loss, we can do stem cell or we can do cell therapy. So we can simply replace those lost cells in our bodies. And so if we have a loss of cells in our tissues, we can just undergo something that's called replacement therapies. All right? And so that's really, really important to understand. And so the solution, of course, then, something that we haven't talked about yet, that mutations can do, is cause cancer. So the way, what really, really happens in our cells, the ends of the cells, like the shoelaces of the cells, have stretches of DNA called telomeres. And when these ends get too short, the cell undergoes a process called self-destruction or apoptosis. And so this is really interesting because there's actually two ways that we can inhibit the telomerase, that we can inhibit it. So essentially, there's two mechanisms that these cells undergo. One is via the telomerase enzyme, and two is via an alternate pathway called ALT. And so what actually happens is when we inhibit this enzyme, this telomerase, and again, there's a bunch of them, but this is like the main one that's really meaningful to understand. And so what happens is when we inhibit telomerase, it doesn't affect the ALT pathway. So there's still going to be some cells undergoing the alternative pathway. And so therefore, if we just do a telomerase inhibitor, we may think, we can just inhibit this enzyme that can completely renews the telomeres, right? Because cancer cells can renew their telomeres. That's how they constantly divide. They can't undergo apoptosis because their telomeres never get too short because they have a telomerase enzyme that renews the telomeres. And some have an alt pathway, so an alternate pathway that they can regenerate their telomeres that's not telomerase dependent. And so just having a drug that blocks telomerase may sound like a good option, and it is. It will slow down the cancer cells, but it doesn't affect the alt pathway. So some will still renew their telomeres via another gene, not a telomerase gene, but they are an alternative gene per se, right? So we know that this alternate mechanism is most likely due to just another gene, not telomerase, but another gene. It's not just has to do with gene expression, but mainly a different gene that renews their telomeres, but not being telomerase. And so therefore, some are just going to use a different gene, and so that's not going to help. And also some may be resistant, right, to the enzyme or to the drug that we use against telomerase. They can literally break it down or prevent it from entering the cancer cells. So cancer cells can prevent the drugs from entering them, as well as they can kind of detoxify it, right, or kind of like neutralize its effect, so making it useless. And so there's actually an alternate approach. It's called WILT. It's called whole body interdiction of length of telomeres. And what this does is you actually completely delete the gene for telomerase. So you get a deletion of the telomerase gene. So essentially we cannot grow unless we create new telomeres or act, right? So not we, but the cancer cells can't grow unless they create new telomeres via telomerase or the alt mechanism, the alternate mechanism. But if we delete the telomerase gene, right? So if we delete the telomerase gene, what's going to happen is these cells are not going to be able to replicate unless what's going to happen is they're going to invent a completely new telomerase due to evolution, but that's very, very unlikely and will not happen within a lifetime. As well as, and I hope that makes sense. Now they could use an alternate pathway as well, and so that's kind of a limitation of that. But it solves the problem because some cells can still survive even if you use a telomerase inhibitor. Some cells may take the drug out and all that. The drug won't enter the cell, and so some you're going to get the small cells that actually don't die, and then they can recreate the tumor or the cancer. So by completely deleting the telomerase gene, we prevent that from happening. The only issue is that there may be another gene, the alt, via an alternative mechanism that these cells can undergo. Having said that, it wouldn't be as problematic because much fewer cells use the alt mechanism, and so we can at least keep the tumors to a very, very small size to make it much more manageable that way. But so some of the issues are that we lose stem cells as they use telomerase, And so, for example, there's a disorder called DK where if we inhibit telomerase, or in this case we completely delete it, essentially we're going to lose cells, specifically stem cells, which we really, really need. So that's really, really a problem, right? And so essentially what can happen is we're going to have to reseed the cells that we're losing, specifically the stem cells, right, into the tissues because they're going to stop dividing because we delete the telomerase. It turns out that can last a decade, 10 years. So that's pretty good in most of our tissues like the skin, the lungs, the gut, etc. So we need to simply replace our tissues, our failing stem cells each decade, right? And we want to give them long telomeres, but no telomerase. So again, we want to give these stem cells. Essentially, we don't want to give them any telomerase to prevent the risk of cancer, but we want to give them long telomeres. So then we just have to simply replace them every 10 years. And so also there has been shown no telomerase lengthening function to the enzyme telomerase. So that's good. So there's no non-telomere lengthening function to telomerase, because if we inhibit the enzyme and it has another useful function, that's dangerous. But it's been shown pretty much its only function is the lengthening of telomeres. So that solves that problem, right? So essentially what we do again is we simply do a telomerase deletion. That's going to prevent cancer from taking place because you don't have the telomerase. Having said that, in some cells you're gonna get a loss of cells, and that's a problem. And so we talk about how we can do that. We can simply do stem cell seeding. We can simply add these stem cells, right? And so that's gonna simply prevent, right? Because when we add the stem cells to the tissues which have long telomeres but no telomerase, we can simply replace that failing tissue every decade. It turns out to be enough because based on the amount of replications that they undergo. The most important are like the lungs, the skin, the lungs and the gut. And others like the heart and the brain, even you don't even have to do it every decade because these cells divide even less often. It's pretty cool actually. This is definitely an important SENS category, and it's also the one where most research is done because everybody is on top of cancer, so everybody knows it. And so even if this wilt pathway, right, even if this deletion of telomerase strategy, the reseeding of stem cells doesn't work, right, this whole body interdiction of length of telomeres, right, where you completely whereby you simply deleted the telomerase gene everywhere in your body, and then replace the stem cells throughout all of your failing tissues over time, over decades we're talking, is a good strategy. But even if it doesn't work, because it is very complicated, there's probably so much research on cancer out there anyways that we can stop this kind of last SENS category from taking place. So it's interesting because it's the mutations mainly causing cancer, which makes them terrible, right? Because there are like non-cancerous effects of mutations as well, like senescence and cell loss, but those can be fixed as per the other videos that I made. We can simply do suicide genes, and we can do stem cell or we can do cell therapy replacement, right? Cell rejuvenation, cell therapy, right? To replace those lost cells. Okay, so it's pretty interesting. That's the wilt strategy. I hope you guys really enjoy it. If you haven't, please subscribe to my channel. Crush that like button. I'll be posting more videos in the upcoming days. Hope you guys have yourselves a great day or a great evening, depending where you are. All the best. Love and power. Bye.